Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh, it's the Science Cafe with your host, Chris Smith.
All right. Let's get started. Good evening, everybody. Welcome to the North Carolina Museum of Natural Sciences. I'm your host tonight. My name is Chris. Thanks for coming out to the Science Cafe on a little bit of a rainy Thursday night. You braved it to get out here to learn something new. That makes y'all my favorite kind of people. You know what? I'm on Twitter a lot, but I was on Twitter, I guess it was maybe yesterday, and one of the regulars in the Science Cafe was responding to a request of cool and interesting science-y things to do. Wherever you're at, they were interested in what's like the coolest thing to do in terms of science. And somebody commented that if they had friends, family coming in, they would bring them to the Science Cafe every Thursday night here at the museum. And the coolest, that's fun, right? Like, that makes me feel good, makes Katie feel good, and makes our bosses feel even better. But the cool thing was that they also wrote they'd been coming to the cafe regularly for a long time, and they felt like they had probably earned a PhD at this point. So I am hereby bestowing honorary PhDs on everybody who's been to more than 3, is that okay, Science Cafes? Is that all right? Some of you are like, wait a minute, we put in a lot more time on this. I am very grateful and appreciative for all of you for coming out tonight. Tonight, we do have a great show for you. We've got a great program. We'll have 2 guest speakers tonight who are both part of the North Carolina PFAS Testing Network. We'll have Lee Ferguson from Duke University and Jamie DeWitt from East Carolina University, who are going to be talking to us about a topic that sounds really fun and exciting, I think: toxic chemicals in human health. That's something that you're all very interested in learning about, right? I think actually, having met them before the show, chatted with them a little bit, I think we are going to have a good time tonight. I think this is going to be a great show, even though the topic at hand might give us cause for concern, maybe gives us pause, maybe gives us something to think about on the way home, and maybe something that we want to keep front in our minds as we continue about our daily lives. And of course, that's what we try to do here every time at the Science Cafe. But I think tonight's topic is going to be especially important and salient, and we're going to have a lot of fun and learn something new. Are you ready to get started? Let's do it. Please welcome to the stage the first speaker up for tonight, Dr. Lee Ferguson.
All right, thank you. Thanks, everybody, for being here, and thank you very much for having me. I'm pretty excited to talk to you tonight about a topic that hits us all pretty close to home, and that is the issue of toxic chemicals and human health. I'm not a toxicologist. I'm a chemist. I'm actually an oceanographer, but I work as a chemist. And so I'm going to tell you a little bit about the chemistry that underlies PFAS chemicals. All right, so PFAS, what is that? That's polyfluoroalkyl substances. And as was mentioned earlier, there's a testing network that's been set up here in North Carolina to assess the occurrence and the fate of these chemicals in all of the drinking water supplies for all of North Carolina. And what's really interesting about this to me is that the discussions and the momentum for that PFAS testing network started right here in this room with discussions that I had with the North Carolina Coastal Federation sitting at this table before we started to discuss options for how to address this with the North Carolina legislature. And they were visionary enough to actually put their money where their mouth was and study this and assess the impacts on North Carolina. Per and polyfluoroalkyl alkyl substances, right? Sounds like a mouthful, sounds like a chemistry mouthful, and it kind of is. So what are these chemicals? There's a bunch of them, and what are they used for? So I apologize for the small wording here, but if you can see, these are chemicals that you're going to find in lots of different consumer applications as well as industrial uses. Everything from non-stick coatings, where we have things like C8 or perfluoroalkyl octanoic acid. All right, this is a chemical that's used in things like Scotchgard, that's been used in coatings, both industrial as well as other materials. There's also grease and stain-resistant coatings, and Teflon. Okay, everybody knows about Teflon. Actually, it's an interesting story. Teflon actually was a government secret for a long time. It was actually used in the Manhattan Project before it was declassified, and now it's used in lots of different consumer products. And Teflon is made using polyfluoroalkyl alkyl substances. So also aqueous film forming foams, right? That's a mouthful. What does that mean? That's actually the firefighting foams that are used to put out things like oil. They use them in airports, etc., right? So, and then everybody has heard about this specific compound here, Gen X, right? What is Gen X other than my generation? Gen X is a chemical that's actually used as a replacement for some of these other PFAS compounds that have been used in industry for a long time. So these are in lots and lots of different consumer applications. It turns out that these Gen X and some of the related compounds are manufactured right here in North Carolina at the Fayetteville Works company down on the Cape Fear River near Fayetteville. And so as chemists, these compounds actually give us a lot of challenges, right? So we end up playing what I like to call environmental whack-a-mole with these compounds. So that PFOA compound, the C8, as I said, it was used in manufacture of Teflon. It's been used in making nonstick coatings for a long time. Well, back in about 2002, the companies that made this recognized that it was actually not the greatest for the environment. It's very persistent. Right? These are compounds that are sometimes termed forever chemicals, right? Because they will be here probably when the sun goes supernova. Okay? They don't degrade. They don't biologically degrade. And so the companies that started making these, they realized back in about 2002 that they should probably phase them out. And what they decided to do was actually replace that chemical with, let's see if this works, with this chemical right here, Gen X, okay? So all they've done is basically put an oxygen in the middle of that chain. It's still a polyfluoroalkyl alkyl substance, right? And that's used to manufacture Teflon and lots of other fluoropolymers, right? So when we get rid of one compound, like this one here, PFOA, we make something else like this, all right? That has similar chemical properties and similar physical properties. So I don't know if any of you remember that old game, Whack-A-Mole. We shut down one type of compound, get rid of it from the marketplace, only to be replaced by something similar. So now, why is this a concern for North Carolina? Well, so it turns out there's lots of different sources for PFAS compounds into the water and into our environment. This includes things like the discharges at the Fayetteville Works plant. There's also application of biosolids that might contain these compounds to agricultural fields, right? And so the Cape Fear River actually right here, starting at the headwaters of the Cape Fear and going all the way down at the Haw River, all the way down to Wilmington, has some very particular sources of these compounds, and we've been studying them as well as some colleagues of mine over at NC State for quite some time now, trying to understand what are the sources, what are the impacts of these compounds. And so actually, here's a good example. This map shows Cane Creek Reservoir, which is actually the drinking water reservoir for the city of Chapel Hill. And so it turns out that there are biosolids applications that happen up here in the headwaters of some of the creeks that flow into Cane Creek Reservoir. Now, who knows what biosolids are? What is it? Well, so actually, in this case, this is actually human-derived biosolids. These are biosolids from a wastewater treatment plant. So this is wastewater sludge that's applied as fertilizer to these fields, okay? And so it turns out that all of the PFAS compounds that are associated with the wastewater sludge are being applied to this agricultural area, and the PFAS compounds are leaching out after the rain and flowing into the Cane Creek Reservoir, right? And so what this does is it ends up increasing the concentration of all those PFAS compounds in the Cane Creek Reservoir and led to high concentrations, elevated concentrations of several of these compounds in the drinking water for Orange Water and Sewer Authority, right? They recognized this and started to add some treatment to try to get rid of that, right? So there's some challenges there. What about Gen X? Well, so the Gen X story broke, I guess, back in about 2014 is when I first started to hear about this. And then in 2016, Dr. Knappy over at NC State realized, and as well as one of his students, May's son, realized that this Gen X compound was actually making its way all the way from the manufacturing plant, right, on the Cape Fear River, down the river to Wilmington, and entering the drinking water supply for the city of Wilmington, right? So, and this was unbeknownst to really anyone because this is an unregulated contaminant. These are unregulated chemicals that are not measured in regulatory compliance studies, okay? So when this was discovered, obviously this led to a lot of concern, both about drinking water safety, about how we might treat the drinking water to remove these compounds, right? And also about the health effects, which Dr. DeWitt is going to talk about in a few minutes. But turns out for this particular set of compounds, it's not just a Cape Fear River problem. It turns out that there were also sources of these compounds to the atmosphere around the plant, right around the Chemours plant, the Fayetteville Works. A precursor to the Gen X compound was released. Turns out it reacts very quickly with water in the atmosphere, turns into Gen X, and then rains out into the surrounding area and has been found to contaminate groundwater wells surrounding the plant. So the DEQ, the EPA, all of us academic researchers are hard at work trying to understand the extent of the contamination problem as well as how we remove these compounds from water. Okay? When it was discovered that we had things like Gen X, things like PFOA, PFOS that were contaminating drinking water supplies around North Carolina, that's when the legislature here got involved and decided to create a network to understand what is the extent of this problem around the state. And so the question was asked, is Gen X only the tip of the iceberg? Well, it turns out there's lots and lots of PFAS chemicals that even the academic laboratories aren't equipped to monitor. Turns out there's somewhere between 4,000 and 5,000 individual PFAS chemicals. And so we're actively working on methods in our laboratories as chemists to try to figure out how to identify these compounds and how to map them out in water supplies, right? So we're spending an awful lot of time trying to understand that. And so on this plot, I guess what I want to call your attention to is Gen X itself, all right? The Gen X compound is only that little red bar right there when we look at the total burden of PFAS compounds in drinking water, right? Turns out there's all these other compounds that we actually don't have analytical standards for and we can't estimate the concentrations, right? But we can see that Gen X is actually a minor component compared to all the other materials that are being released from this particular discharge. Okay, so what are we doing? What are we actively doing to try to solve this problem? So the PFAS testing network was set up, as I said, about a year ago. We've been at this for about a year. And so our part of that project at Duke University and at NC State and UNCC is to ask the question, so what can we learn about PFAS occurrence and exposure in drinking water? Right? How much of this material is getting into drinking water and where is it happening? Okay? So we asked the question, what are the concentrations of both the legacy PFAS compounds, those have been used for many, many years in products, as well as emerging PFAS compounds like Gen X, all right, and some of the other related compounds in North Carolina public drinking water sources. And so what we've been charged to do is actually go out and sample all of the public drinking water sources around the state of North Carolina. This adds up to about 400 different sites around the state, all right, and test each one of those for PFAS concentrations and occurrence at least twice over the next, really about 6 months we have left of the project. And then for those that we actually find elevated concentrations, we're going to go back and do a third and possibly a fourth round of sampling to understand in more detail what the concentrations and what the burdens are. So we're engaged in this research right now. The way we do this is with analytical chemistry. Okay, so those of you who are, who's a chemist in this room, by the way? All right, okay, so Not that many, but a few of you. So those of you who aren't, think back to general chemistry way back. And so one of the real challenges with this type of work is to detect concentrations of trace organic compounds like these PFAS molecules in a really complex mixture, right? So we're doing a sophisticated analytical chemistry using an instrument called a mass spectrometer, right? And so those are the techniques that we can use to measure these compounds in water, because PFAS in water, you can't smell it, you can't taste it, and you certainly can't see it, okay? So the only way that we can detect these compounds is with analytical chemistry. So what have we found? We've got a couple of what we call exceedances that we've seen to date. So we're about a quarter to a third of the way through the first round of sampling at this point. And we've observed two specific exceedances, right? One of them we actually weren't terribly surprised by, and that was the Orange Water and Sewer Authority, OWASA, exceedance. They knew about it. We knew about it. We knew that these PFAS compounds were getting into the headwaters of the Cane Creek Reservoir because of biosolids application, most likely. But we were also surprised by an exceedance that we observed in Maysville, North Carolina. Okay, so this happened May 7th when we took the sample. May 7th, we took a sample of the drinking water supply from Maysville. And we were quite surprised to see elevated levels of PFAS in that specific sample. Okay, so we notified the two utilities. We gave them some data. So here's the example of the OWASA data. Okay, this is Orange Water and Sewer. What these bars indicate is actually concentrations of the individual PFAS compounds. So the dashed line right up here is what EPA considers their health advisory level of what they consider to be a safe level of PFAS in drinking water, okay, with respect to toxicity. Dr. DeWitt will talk about that. And that dashed line should not be exceeded by this compound and this compound combined. So if you put that bar on top of this bar, it just barely exceeds that dashed line, okay? So in this case, that concentration in the raw water was higher than expected and higher than what the EPA sets as a safe drinking water level. Okay. Now, Orange Water and Sewer had already known about this, and they've already instituted treatment measures to bring those concentrations down by almost tenfold. Okay. So drinking water in Chapel Hill. Anybody here live in Chapel Hill? Okay, it's safe. So with respect to PFAS, if you believe that 10 part per trillion is safe. So they're able to bring those concentrations down by a factor of 10. I live in Chapel Hill also. I was very relieved to see this. What about Maysville? Well, so Maysville, turns out, even for individual compounds like PFAS, and this is the hexanoic sulfonate, right? These individual compounds are above the health advisory level, all right, for these PFAS compounds. So, and this was quite a surprise. So, who knows where Maysville is? It's in Jones County. Sorry. Yeah, Jones County. It's in eastern North Carolina. It's somewhere between Jacksonville and New Bern, basically. I actually took this sample. I don't usually go out and do this. Usually my students are doing it, but this is the one sampling event that my students let me do. And of course, it had to be the one that we found the exceedance with, right? But so Maysville, North Carolina, is a very small town. They get their drinking water from the Castle Hayne Aquifer, right? The groundwater source. All right, minimal treatment. They treat it with chlorine to disinfect. All right, and then they distribute it. And it turns out, actually, the drinking water concentration, the finished drinking water concentration, we found out later, was almost exactly the same as what's in their raw water. So the treatments that they're doing were not intended to remove any of these PFAS compounds. Of course, the big question is, where is this coming from, right? We were able to figure out a couple things. First of all, it's not aquifer-wide contamination. Castle Hayne Aquifer is actually pretty clean. All of the other sites around Maysville, Jacksonville, Pollocksville, Vanceboro, we went down the Crystal Coast, did Beaufort, Morehead City, Atlantic Beach, Newport, they were all clean. It was only this one site in Maysville. It turns out that the site is located not terribly far away from their fire station, and the signature of the PFAS in this particular sample is very indicative of a source from aqueous film forming foam, which is the firefighting foam, right? So we're still trying to figure out exactly what happened and when and how But once we notified Maysville, within 7 days of collecting the sample, we'd analyzed it, we called them on the phone, we sent them these plots, they immediately switched over to Jones County water, right? I drove down, grabbed a sample of Jones County water, brought it back. Within 24 hours, we were able to tell Maysville and Jones County that the Jones County water was completely devoid of PFAS. So they were able to take affirmative and specific steps to relieve the exposure of their residents to these PFAS compounds after understanding that they're present, just by switching their water source to Jones County. Okay? And so this is the work that we're engaged in, trying to understand the extent of these chemicals in drinking water supplies around the state of North Carolina. And so we're hard at work in my lab, also in NC State and UNCC. My students do nothing but drive around North Carolina these days, taking water samples. They don't let me do it anymore, apparently, because I tend to be bad luck. And so, but we're trying to cover the entire state, and we're going to make all this data available. Okay, it's all going to be publicly available when it's finished, and so you'll all be able to check your water supply for concentrations of PFAS. Okay. Okay, so now I'm sure all of you are asking so you're all asking the so what question, right? I mean, here I am up here telling you this stuff's in the water. I'm a chemist, right? If you want to know what this stuff actually is capable of doing, what is the implication of having this stuff in the water, I'm going to hand the microphone off to someone who's much smarter than me, and that's Dr. Jamie DeWitt from ECU. Please welcome her to the stage. And she's going to tell you all about the effects.
Hello, how is everybody? I drove all the way here from Greenville, and it wasn't too rainy. So I'm very happy to be here. All right, I have a question for you before I get started. Let me go to the next slide. How many of you have PFAS in your bodies? Everybody needs to raise their hand. Everybody. Everybody. Really about 98 to 99% of people in the United States have PFAS in their bodies. Where does it come from? What's that? Popcorn, so it can be in food contact materials to prevent grease from leaking through. But where else do we get exposed? Dental floss. What was that? So the coating from nonstick pans is made with PFAS, but your exposure is probably fairly low. How it's produced likely contributes more to your exposure. Well, what did Dr. Ferguson just talk about? Water. So drinking water can be a major source of our exposure. But we're finding out now that we can get exposed via air. These compounds can absorb through our skin, but food is thought to be one of the major sources of exposure. All right, so we get exposed to these chemicals. They're inside of our bodies. What do they do? Well, look at that big list. The Agency for Toxic Substances and Disease Registry, which is a quasi-governmental agency that is led by the Centers for Disease Control and Prevention, compiled data from all sorts of studies. And this is the list of positive associations that they have found in humans. So this is from epidemiological studies of people from highly exposed areas, from people who work with PFAS, and then from people like you and me, people in the general population. And that's a pretty lengthy list. So what does this list mean for you and for me? Well, it means that there is an increased risk of certain types of health effects if your exposure to these compounds exceeds, well, according to the US EPA, 70 parts per trillion. According to some other states, that level should be much, much lower, maybe around 10 parts per trillion. Dr. Linda Birnbaum from the National Institute of Environmental Health Sciences recently said maybe that level should be as low as 0.1 parts per trillion. So we have data from a huge experiment. And that experiment was one of these particular PFAS getting into the drinking water of a community in Ohio and West Virginia. And this was from a plant that produced PFOA and other PFAS. PFOA, or perfluorooctanoic acid, was in the water. and over 70,000 people, or just under 70,000 people, became guinea pigs in this giant PFAS experiment. They hired epidemiologists to study them. They were part of a class action lawsuit, and they decided, you know what, we want to know what this stuff is doing to our bodies. And so from this giant epidemiological study, we found that PFAS can have effects on cancer. So kidney and testicular cancer are one of the health effects that's associated with PFAS exposure. Thyroid disease, ulcerative colitis, which is an autoimmune disease that can impact your intestines. Elevated high cholesterol, or elevated diagnosed cholesterol. We also have seen changes in pregnancy outcomes, so pregnancy-induced hypertension and preeclampsia. We also have some additional data from other epidemiological studies to indicate that the immune system can be impacted. So if you're exposed to high concentrations of these compounds and get a vaccine, there's a probability that that vaccine won't be as effective as it should be, which means that your immune system isn't doing what it's supposed to be. Now, we have these studies from humans. Humans are very different. We're variable. So epidemiological studies can only produce associations, right? We say that they don't demonstrate causality. So we have animal data to back up these findings in humans. And we see many of the same types of effects in animals. We see changes in thyroid hormone. We see changes in pregnancy outcomes. We see changes in the immune system. We see cancer. We see effects on liver health. So these compounds are able to produce adverse health effects. They are toxic. So not only are they persistent in the environment, not only do they move from the environment into our bodies at certain concentrations inside of our bodies, they can produce these adverse health effects. I think it's pretty scary. Would you agree? These are synthetic compounds that are produced to make our lives better, but because of their production, we have been exposed to them. And the accumulating evidence that we have indicates that they can produce effects in multiple organs in our bodies. So they are systemic toxicants, but they can also produce effects on specific organs. So they're target organ-specific toxicants as well. So they can affect the liver, but they can have effects on other systems in our body. So what are we doing as part of the PFAS testing network to understand what's going on with our health? Well, I am co-leader of Team 5, and we're asking a lot of different questions. We're asking questions about how many PFAS and what kinds show up in landfill leachate. So when we dispose of products that are made with PFAS, do those PFAS compounds show up in landfill leachate, or the water that leaks out of a landfill? And can we get exposed to those? We have Dr. Scott Belcher, who you all probably heard, looking at bioaccumulation of PFAS into alligators and fish. In my laboratory, we're asking questions about immunotoxicity. Dr. Owen Duckworth at NC State is asking about the ability of PFAS to move into plants that we might eat for food. And then we have Dr. Rebecca Fry from UNC Chapel Hill asking questions about how PFAS can impact the placenta and whether or not that will have impacts on pregnancy. And then we have a professor from NC A&T, Dr. Nicholas Luke, who's going to generate some models so that we can better predict where PFAS will go in our bodies and what they can do once they're in our bodies. So in my laboratory, we're asking questions about the immune system. And we're asking 3 basic questions. Are there effects on the adaptive immune system? And that's the part of the immune system that works to protect us when we get vaccinated. We're asking questions about the innate immune system. So we're asking questions about whether or not these cells called natural killer cells can kill other cells. They play a really big role in protecting us from cancer. And then we're asking questions about the numbers and types of different cells in the immune system, and are there impacts? So when we think about the immune system is designed to protect us from non-self agents. But it also plays some really important roles in homeostasis, in maintaining what our body is supposed to do on a day-to-day basis. Plays a really big role in making sure that if we have any cells that mutate, that they don't turn into cancer. Well, sometimes the immune system gets really excited and does more than what it's supposed to do. So anybody suffer from allergies? Yeah, that's an overactive immune system. So there's an increased risk of allergy and asthma with exposure to PFAS. So on one hand, in some people, they make your immune system angry and work it up. On the other hand, they can suppress the ability of the immune system to do what it's supposed to do. And this is where we see decreases in the ability of the immune system to make antibodies against vaccines. Well, when this happens, the immune system isn't doing what it's supposed to be doing. So we call these compounds immunotoxic. They can enhance the immune system when it shouldn't be enhanced, and they can suppress the immune system when it shouldn't be suppressed. This is what immune suppression looks like in a mouse model. This is from a study that we did, well, that I did when I was a postdoc in 2005, and we published it in 2008. What we can see, I don't know how this little digital pointer works. Well, what we can see with the asterisks, that's immune suppression. So these are mice that were given an antigen. We gave them sheep blood. They made antibodies, and they didn't make enough antibodies in those groups where they're exposed to PFOA. This is what immune suppression looks like in humans. This is a study by Philippe Grandjean, who's a professor at Harvard and the University of Southern Denmark. He demonstrated that children who were exposed in utero did not develop appropriate vaccines to diphtheria, and so they weren't appropriately protected. So PFAS are immunotoxic. And when we think about the body of evidence that we have for PFAS from humans and from animals, we can conclude that they're immunotoxic. There are some other steps we can take to evaluate other types of immunotoxicity if, for example, the vaccine response isn't impacted, but the vaccine response is one of the most robust measures of the immune system's ability to do what it's supposed to do. So when we see suppression in that tells us that the compounds are affecting the immune system. In 2016, the National Toxicology Program looked at all of the data associated with PFOA and a related compound, PFAS, or perfluorooctane sulfonate, and they concluded that the evidence was sufficient to classify these compounds as presumed to be immunotoxic to humans. So we are very confident that these compounds affect the immune system. And as I demonstrated earlier, they can also be associated with additional effects. And oh my gosh, I am boiling. I'm very shiny right now. All right, so I think this is the point where we can answer questions.
Hold up. Thank you for your question. But I want to let everybody know the way the Q&A works. I'll bring you a microphone. That way everybody in the room can hear, and anybody who's watching online can hear the questions as well. So I've got a mic. Anu here helping me has a mic. We'll bring the mics around the room, so wave at us if you've got questions. Y'all look for me, look for Anu for who's got the next question. And you absolutely get the first one.
You mentioned that the Orange Water and Sewer Authority took action to, I think you said, a 10-fold decrease in the PFAS in the drinking water. What exactly did they do, and how quickly were they able to do that?
Sure. I can tell you briefly how this happened. So there was no monitoring required for PFAS compounds up until the EPA entered what's called their Unregulated Contaminant Monitoring Rule, or UCMR 3. In that specific case, the EPA added PFOA and PFOS to the list of chemicals that the large utilities are required to monitor. This happened, I guess, about 4 or 5 years ago, something like that. Orange Water and Sewer Authority was one of the utilities around the area that actually got a positive hit. So they saw, hey, look, we've got elevated PFOS and PFOA because of because of the biosolids. When they realized this, they immediately started to take steps to add activated carbon treatment. In the case of Orange Water and Sewer Authority, they added powdered activated carbon, or PAC. And so activated carbon can help to absorb some of these compounds and remove them. It works really well for the longer chain PFAS, the larger PFAS. Things like Gen-X and some of the shorter chain PFAS that are more water soluble, they're very poorly removed by things like activated carbon. Okay, so it's actually much more difficult to remove them using those technologies. The best practice for taking these out of the water, if you ask me what I do with my water, I use reverse osmosis. So under sink reverse osmosis system removes almost all of these PFAS compounds. Problem is, it's very expensive to do on a utility scale. So the utilities are trying to use adsorptive methods to try to tackle this. And that's what Cape Fear Public Utility is working forward.
Oh, and just a quick follow-up. And you mentioned about the biosolids or sludge in the vicinity of the watershed. So there's sludge applied throughout the state. What is it, the specific sewer treatment plant that's providing the sludge that had the problem that ended up by chance being applied in Orange County?
So at the risk of making a very broad statement, I will say this. Pretty much any biosolid, any municipal biosolid that you use in this country will be contaminated with PFAS. It's not just, so actually in the case of Orange Water and Sewer in the Cane Creek Reservoir, that's Burlington sludge that gets spread there, okay? But it's not just because Burlington has high PFAS. Okay, these PFAS compounds, when they're in the wastewater, many of them are going to adsorb to the sludge. It doesn't matter which treatment plant it is, because we're all using these materials all the time in our daily lives. So in general, and so this isn't just a North Carolina thing. There's all over the country, biosolids are certainly contaminated with PFAS. It depends on the specific drinking water treatment and hydrology sort of regime as to how much of it ends up getting in reservoirs. But certainly biosolids that have PFAS are not unique to Orange Water and Sewer.
Thanks to both of you, and a question for Dr. DeWitt. So nice to see the studies that show both correlational and causal impacts or associations. But I'm wondering if you can take us farther, perhaps down to the cellular or molecular level, to help us understand why these compounds have the immunotoxic impacts.
Oh, I wish I could answer that. And that was a really smart question. So you must know a lot about science. So the cellular effects of PFAS are yet to be fully unraveled. We know that they can stick to proteins. So they're in high concentration in the blood and in organs that receive a lot of blood. So they stick to albumin and they can stick to other proteins. We also know that they can interact with a subcellular receptor known as the peroxisome proliferator activated receptor alpha. PPAR alpha, it plays a role in inflammation and lipid regulation. We also know that PFAS can interact with mitochondria, which are the little powerhouses of our cells, and they can increase reactive oxygen species. So that can damage cells because of this reactive oxygen species generation. We also know that they can be endocrine disruptors, so they can impact levels of testosterone. One of the reasons that we think they induce testicular cancer is that they can increase testosterone, which can act as a growth promoter. And so if you have Leydig cells, which is the type of cell that develops cancer in the testes, you can get promotion or extra growth of those Leydig cells because of the testosterone being overproduced. In terms of the immune system, we know that the deficit lies in B cells. And so B cells in the immune system are the cells that produce antibody. And if I get funded for a grant that I've submitted recently, we'll be able to ask questions that kind of combine some of those mechanisms into asking, why don't B cells make the amount of antibody that they're supposed to make? And that's what we're trying to figure out. But a specific molecular mechanism to unify our understanding of toxicity of PFAS still remains elusive.
My question's for Dr. Ferguson. So you talked to the Maysville Fire Department, or the water treatment, but did you talk to the fire department to tell them to switch from AFFF to fluorine-free foams?
Well, so, I mean, I haven't told them specifically to do that, but I have had conversations with the town manager, the water utility. I mean, this is a community of only 400 people, right? So it's not a very large facility. But I've talked to the town. They had a town meeting that I actually spoke at via Skype, And I've had some email discussions with the fire chief. He actually sent me a photograph of their stack of AFFF that's in their firehouse. And so, you know, I think that they're aware of the problem at this point. I'm confident that, you know, the fire station wants to avoid any further, you know, contamination of the water systems. I think it goes well beyond Maysville in this case, because you know, we've all, as a scientific community, we've thought about this contamination from the AFFF as mostly a problem on military installations, because that's where most of it's been noticed. Only recently have we started to discover that, hey, wait a minute, you know, even small, you know, village and town fire departments use these materials as well. And in the case of Maysville, I actually noticed in the photograph that at the bottom of the stack was a carboy of what's called 3M light water. This was the original AFFF that was manufactured by the 3M Corporation and phased out in 2002 because of the presence of these chemicals that, you know, PFOA and PFOS. Well, you know, fire stations that don't use a lot of AFFF may still have, you know, this stuff sitting around from 15 years ago. Whether they pull it out and use it, I don't know. But even the new generation AFFF that's not fluorine-free still contains PFAS, different types of PFAS, not PFOA, not PFOS. It's a complicated problem. And what I can tell you is that most of the military installations are moving towards a system where they don't use AFFF, fluorine-containing AFFF in their training activities. Okay, and so also municipal airports are working towards that as well.
Thank you both. I have a question about the health effects. Can you help us to put some context around the overall impact of these chemicals? How does it compare to some of the other pervasive pollutants that we're all exposed to, secondhand smoke, bad urban air quality, all the other things that are, you know, compromising our immune systems?
Oh, you're asking me to remember specific levels from toxicology when I was a graduate student. So the exposure level that the US EPA has determined to be acceptable is 70 parts per trillion. That's pretty low if you think about it. So let's think about lethal doses, LD50s. What do you think is a really bad LD50? A really high number or a really low number? A low number, right? So it takes less of that compound to eliminate 50% of test organisms. So botulinum toxin has a very low LD50. Ethanol, by comparison, has a relatively high LD50. So let's think about arsenic. So does anybody know what the safe exposure level for arsenic is? It's been debated, about 10 parts per trillion in drinking water. Arsenic is a ubiquitous compound. It's ever present in the Earth's crust. So if we compare PFOA and PFOS to arsenic, doesn't really seem like they're that terrible. I mean, it's seven times higher. 70 parts per trillion is 7 times higher than the arsenic concentration. But I think something that we have to think about with PFAS is that they have these additional characteristics of being persistent, of being very easy to move from the environment into our bodies, and they're also highly mobile. So a lot of compounds that we consider to be persistent organic pollutants, like dioxins and PCBs and polychlorinated biphenyls and DDT, they're not really mobile. They like to stick to sediment, and once they're in our bodies, they stick to the fat. We also have to think about the number of PFAS. We've got about 5,000, as far as we know, individual PFAS. If we think about the number of polychlorinated biphenyls, there's 209 different PCB compounds. So we're exposed to a huge number of PFAS. So in terms of the relative risk, I don't really know if I can answer that question, because we're exposed to a suite of PFAS, and to something like arsenic, we're exposed to 5 different types of arsenic, if we think about the different valence states of arsenic. So I think this question really we need to start thinking about PFAS as mixtures and managing them as groups of compounds as opposed to individual compounds. So I didn't really answer your question because I don't really know if I can appropriately answer that. We can't really put it into context until we understand a little bit more. But I hope I gave you at least a little something to chew on.
What's the best source of information if you happen to be in another state? If you want to get comparable information from other states, is there a central source of
So in terms of health effects?
no, actually in terms of what's there.
Yeah, unfortunately, your best source is actually the results from the Unregulated Contaminant Monitoring Rule 3, UCMR 3. So that's the EPA's Safe Drinking Water Act. So they and all that data is public. But what it's going to tell you is basically, you know, whether it was above a certain threshold or below, and that's only required for large drinking water systems. So, and I can't remember what the threshold here is for large.
Seattle?
Sorry? Maybe it is 25,000, yeah.
I mean, I'm just curious, if you live in, say, Washington State and Seattle, how do you find out what the comparable situation is?
Environmental working group? Yeah. So, I mean,
Environmental working
yeah, and I mean, and it really depends on the state. I think, and there's no, I mean, I would say there's no very comprehensive database out there right now, because these compounds are still, I mean, I would stress this, these are considered unregulated contaminants, okay? PFAS are one class of unregulated contaminants, and so we've focused on telling you about this one compound class right now, but, you know, my soapbox, if I'm allowed to step on it for a minute, is that there are somewhere on the order of 85,000 chemicals in commerce right now, right? Does anybody know how many compounds EPA has ever banned because of toxicity? How many do you think?
5.
Well, luckily they did a little better. It's 9.
Oh, okay.
9 chemicals. Right? How many chemicals are considered to be toxic pollutants by EPA? In water. Toxic pollutants in water. Do you know? It's 126. 126 chemicals. That's it. Out of 85,000, right? How many chemicals have ever been tested for toxicity? Yeah. So, well, how many chemicals are there? How many organic chemicals are known? Does anybody know that answer? Huh? Synthetic organic chemicals are known. Anybody hazard a guess?
Where'd those 2 chemists go?
Yeah. 10,000? Actually, it's somewhere on the order of 80 million. So that's what's in PubChem. So being able to kind of understand, so just to get back to, I'm sorry, I'm not trying to just go off on a tangent here, but to specifically address your question, it's very, very difficult to find compiled databases for chemicals like PFAS, unregulated chemicals like PFAS in water on a national scale. North Carolina, I mean, I will say, this PFAS network is the most extensive program of its type ever attempted in the United States. And I would say probably the world. The only one that's more comprehensive is a program on the Rhine River in Switzerland, and that's. But you know, the Swiss got a lot more money than we do. But you know, you should all be actually, and I will state this. You should all be quite happy with the steps that were taken to do this study, because nowhere else in the United States do we have this kind of effort going on to try to understand this exposure. And I feel very strongly about that.
I want to point out real quickly that you can go to the Environmental Working Group website in partnership with Northeastern University. They've made that unregulated contaminant monitoring rule data available. So you can click on the map, and you can even click, I think, on your zip code and find out what those concentrations are for PFAS. So if you just Google, sorry, I shouldn't. If you just search for Environmental Working Group and Northeastern University, you'll get the PFAS information.
Hi. I have a question for both of you, because you both are obviously experts. And I feel as though the question is already in the air, and it's slightly depressing in the sense of like what is to be done, even though we have the data, we have the research. And obviously you're invested in making this data public, making it free. And so are you working with policymakers? Are you working with local activists? Are you working with government? Should I even drink water? These are my questions. And also, once I swam in the Rhine, I don't know if that's a good or bad thing. So, like.
Well, I think both of us have very specific positions and opinions on what should happen with PFAS, and I think both of us work to a degree with various organizations at the political level to try to ensure that our scientific data is used to make decisions. But I'm also a human who is exposed to these compounds. I actually bought a pair of hiking pants recently and waded across a stream, and the water just rolled off. And I went, oh no, what's in them? So I think as consumers, we have the power to make a lot of choices. We can educate ourselves, find out what products contain PFAS, and choose not to buy them. For example, I need new carpeting for my home, so I'm going to go with manufacturers that I know have pledged to be PFAS free. I'm switching my brand of dental floss as soon as I finish using up the PFAS contaminated dental floss because it's expensive. So we can make educated decisions about what to purchase.
I think that's right on. I mean, the only thing I would add to that is, so I have a saying that I'm fond of, and that is that sunlight is the best disinfectant. And so what I mean by that is that if you shine a light on something and you really make it public and you expose it, then the pressure that can be brought to bear by you can make real change. So one of the things as an analytical chemist that I've been passionate about in environmental chemistry is to make everyone aware of what exactly is happening with the chemicals that we use and that we dispose of and where they go. So we do something in my lab called non-targeted analysis, and so that is intended to blow the doors wide open on understanding what is in our waters and what is in our exposures. Okay. Now, of course, I leave it up to people like Jamie to tell us, what does that mean? But, what I want to be able to do is to shine a light on the presence of these compounds in the environment. All right. And so what I found is that policymakers will listen when they hear from you. So Jamie and I are scientists, and so what I try to do is the very, very best science I can do in my laboratory, so that I can put the data out there and let the policymakers do something with it, with the pressure that comes from the public.
This is just more of a philosophical question. Where's the logic in making forever chemicals?
I mean, I can speak to that. Yeah, so there's a reason I mentioned environmental whack-a-mole, right? So this isn't the only compound class that we go through that with. Another great example is brominated flame retardants and flame retardants that are in products, right? So there are certain chemistries that are innately suitable to specific applications, okay? So there are things that PFAS chemicals can be used for and where nothing else can. So for example, solvent and chemical resistant containers for doing reactions. Also things like metal plating, all right? So if you're going to do certain industrial processes, there are no other chemistries. There's a reason why these chemicals are forever, and that's because they're so resistant to chemistry. So you can do things like add strong oxidizing acids to them and nothing happens. And so there are very few other chemistries that are suitable to that kind of process. What we need to do, though, is actually put a lasso around where the essential applications are for those. I would not advocate for the complete absence of fluorine chemistry, but what I would advocate for is a responsible use of that chemistry.
Well, this is sort of a follow-up question to an earlier one, but I was more specifically about how you interact with the political forces that regulate these things. The Department of Environmental Quality in North Carolina has a water resources department, and I just wonder if you interact with them.
Very much. Yes, absolutely. In fact, I mean, I'll hand it off to you in a minute, but one of the things that we've done as part of the PFAS testing network is help to, I would say, transfer technologies sometimes to the DEQ, the Division of Water Resources. So they've just bought a mass spectrometer with funding from this program, from the General Assembly, to specifically target these chemicals in water supplies. And what we've been doing is working with the Division of Water Quality and Division of Water Resources to transfer the methods that we've developed for measuring these chemicals in water directly to their laboratory. They bought the same mass spec I have in my lab, right? And so we've had their chemist over a few times to learn to transfer the technologies. And so, yeah, we're working as closely as we possibly can with DEQ.
And I talk with the toxicologists. We don't talk as regularly as I think that we would like, but we talk a lot about the toxicology. What do the health-based values mean? What particular endpoints are going to be most protective of human health? And then I've also talked with them so that they could advise me on what particular compounds here in North Carolina I should study in my laboratory. So I would like to talk to them more often, but we're all busy.
Hi. I know you said that they are in the air too, and I wondered about the mechanisms for how they're getting in the air, and also is the air quality being tested?
Yes, yes, and yes. So, so the first answer to your question, I think, is one of the most interesting chemical stories that I've ever heard. In fact, I actually used this as the question on the qualifying exam for the graduate students in my department this last year. So, and it gave them hell, I'll tell you that. But so it turns out that the manufacture of these chemicals uses a precursor that is what's something called an acyl fluoride. And so anyone who's an organic chemist knows that acyl fluorides are one of the most reactive chemicals that can be made. And so they hydrolyze very fast. That means they react with water almost at a diffusion-controlled rate. That is, as fast as the water contacts the molecule. And so now Gen X is completely non-volatile. All right, it's not volatile at all. It stays in water. But the acyl fluoride, on the other hand, is a volatile molecule. So what was happening is during the process, they were accidentally blowing this stuff up the stack. It gets up into the atmosphere, and then it reacts with, I mean, we're in North Carolina, right? So the humidity, it reacts with the water and turns into Gen X and rains out. So that's how it was getting into the air, and that's the mechanism for it getting into the groundwater. As far as the caveat is we can't, it's hard to prove that, but there's really no other explanation. And we're still trying to figure out, and the DEQ is actually doing most of this, exactly how far around the Chemours plant, the Fayetteville Works, this went. As far as air testing, we have an entire team in the PFAS network that's devoted specifically to air testing for these compounds. And we also have a groundwater monitoring program within the network. We're trying to cover all our bases. We can't do everything, but we are trying to keep a handle on this.
After that answer, I kind of want to say, Lee, could you tell me in my laboratory what enzymes I would evaluate to understand PPAR alpha agonism by PFAS? Because that was a very smart person question.
Sorry, I don't know that one.
Let's give him one more round of applause. Thank you very much. And hey, thanks to all of you for coming out to the Science Cafe tonight. I know that you learned something new. I know that you've got something to think about on your way home, and that will at least get you through to next Thursday night at 7 o'clock right here at the Daily Planet Cafe, where we'll be back with another exciting topic. Check out naturalsciences.org for all the cool stuff that's happening here at the museum every day of the week. And do me a favor before you leave tonight. There are survey forms on all the tables. If you could take a minute or two, fill that out for us. That is a huge help to make sure that we're giving you the programs that you want. This is your state museum. We want to make sure that we're giving you the science cafes that you want to attend. Thanks, everybody. Travel safe. Have a great night. Bye, everybody.